Okay, good morning, everyone. Let's get started. So my name's Ed Blucher. I'm the director of the Fermi Institute that hosts these lectures. I'm very happy to welcome you to the 97th of the Compton lectures. They started in 1976. And I'm very pleased to introduce the spring lecture for 2026, Keith McBride. He was an undergraduate at Bowling Green State University in Ohio and did his graduate work at Ohio State. And since 2023, he's been a Granger Fellow in the physics department here and in the Fermi Institute. And he's going to tell us about using particles from space to learn about our world. So I think you have a fascinating set of lectures to look forward to. So thanks.
Thank you so much. Assuming you can hear me, I'll talk as loud as possible, but let me know if you can't, because there's no point in me talking if you can't hear. The whole reason I'm here is to give you guys a great lecture. So, again, thanks. Pleasure to be here, give these lectures. I'm going to jump right in today and tell us about, what astroparticles are. Let's see if this works. Yeah, astroparticles, what they are, how we can use them to understand the cosmos, and they're going to tell us an interesting story and just reveal to us interesting things that normally not possible to see. So we're going to jump right in. Does anyone know what this is an image of? Some of you in the crowd probably don't know, and that's okay, but I'm looking at a few very specific people that probably should know what this is an image of. So this is an image. It's the same picture, actually, same region in space as this. Does anyone know what this is an image of? That's okay if you don't. So this is the same picture with a different lens. Both of those are the same picture, essentially as the center region of this, which is the Milky Way galaxy. This is our galaxy, the view in the optical or the visible light of the Milky Way galaxy, right? And so you can see a few things here, right? There's a bright center and then dimmer on the edges, right? And so that central region is those other two photos, right? But you wouldn't know that originally, right? Because there's different features, there's different structure inside. And to understand what happens when you put on different lenses to look at the universe, we're going to have to learn about the electromagnetic spectrum, right? And so this is something that you might have been taught, that the electromagnetic spectrum, all of it is light. On the left side, we have radio waves, which you might know from listening to your radio. In the center, we have that visible light, right? That's what you use with your eyeball. That's what you see. That's what we use with the Hubble Space Telescope that gives us these wonderful photos of the universe. And then at the highest energies, we have X-rays and gamma rays. And at the highest energies here, we're looking at more energy to the right. We go to the highest energy kinds of light we know of, the gamma rays, are at the shortest wavelengths, right? And so radio waves are low energy but long wavelength. And the energy at the highest side, gamma rays, are very short wavelength. Okay, and so these are the things that we're looking at with those three images: the optical in the center, the radio waves, low energy but long wavelength, and then at the highest energies we have X-rays and gamma rays. But what happens when you put on these different lenses is really interesting. You can take, for example, a picture that you look at. The shiny object is called an instrument box that we recently flew on one of our cosmic ray detectors in Antarctica. And what happens when you look at it right now, it just looks like a shiny metal box. But if you go to the infrared, you can see that there's a hot spot on the instrument box here on the right? Something that's not visible, but totally accessible now to you. Your understanding changes because you've used a different lens. Okay? And this is really important. So if we go back to the optical image of the Milky Way, and we look at the radio waves, we're looking at the center of the Milky Way, and we can see things that we can't see with the optical, because the kinds of processes that are going on underneath is hidden by this optical emission, right? If you just look with your eyeball, you won't be able to see hidden structure, different regions, these long filaments, strange features. And in the X-rays, right, you can see different things. You can actually see through opaque objects, right? With radio waves, you can see different processes going on, and you can reveal hidden structure. But before we talk about exactly what's going on with these different lenses, how you can use them, you have to first ground yourself with a background and understanding of why those things are bright at different wavelengths, right? So what makes an object bright? This is just a review for some of you, and for a lot of you, this is how astronomy sort of is born too, is that the temperature and size together determines the brightness of an object. So you know that this might be from some of you, younger audience, you don't know what an incandescent light bulb is because we don't use them anymore. This is actually a light bulb that has been on for over 100 years. It's called the centennial light bulb. It's a metal filament in the center that has electric current running through it, producing light, right, because it's at a hot temperature. It's over 4,000 degrees Fahrenheit. Not nowadays, because it's been on for so long, it's sort of decayed away a little bit and it's not so bright anymore. But you know that the thing is hot, so it glows. And that's why it's bright. But the other thing you know is that the size of an object determines its brightness. So the biggest star we know of in the galaxy, I think it's probably the second biggest now, but basically one of the largest stars in the galaxy is Betelgeuse. It's a giant red star, and you can see the size of it here compared to that of our sun. It's ginormous, right? But Betelgeuse isn't as bright as the sun, even though it's much, much larger. And that's because the sun is so close. Betelgeuse is so far away. And so the reason these things look bright to you is either you're close to it, or it's hot, or it's large. Those things together make an object bright. So when you take those images of the Milky Way, right, you can see that the brighter the object was, or the hot, it's probably from being hotter. It might be because it's so large, or it could be because it's so close. And just as a side note, Betelgeuse is actually 30 million times further away from us than the sun. But it's still very bright in the sky because it's such a large star. And you can actually look at different colors when you talk about the brightness of an object. You can look at different colors, right? You can look at different wavelengths of light. And so when you look at the sun, for example, there's many different colors emitted, from red to blue. And on this plot on the right here, we know this via Wien's law, that where the peak emission happens, right, tells you how hot the object is. So that's something you can learn by looking at the different colors in the visible light of what the temperature is of an object. And so this is where you should know this from your experience maybe too, but something that's typically said nowadays is the bluer things are hotter, right? And that's true of a flame. When you have the red region, the blue central region of a flame is hotter. And that's because there's more energy there. There's smaller wavelength, right? So if you compare two of these incandescent light bulbs, the one like the centennial light is actually not as hot as some of the other incandescent light bulbs that appear white. So hotter, shorter wavelength. Okay? And this is all thermal emission. This is how you can understand the world with your optical lens, right? And this is what we sort of know to be bright. Objects like the center of the Milky Way is bright because it has a hot temperature, it's large, and maybe it's relatively close by compared to other things. But there's actually different kinds of emission that we need to talk about. All right? There's not just thermal emission. There's also ionization of gas from really strong fields, such as electric fields and magnetic fields. Okay? And so this is where you get something like a neon sign. You might know this from your experience with neon signs, is that that's not hot filament. That's not hot metals anymore. This is us ionizing neon gas in a chamber, and the ionization of the gas gives you quantized energy levels that produce different colors. But now it's not a spectrum of continuous colors. This is now very specific colors coming from a different process entirely. Okay? And actually, I would like to point out, this still holds. If you're closer to that neon sign, it's going to appear brighter to you. And I'd also like to point out this neon sign example is one of the oldest that I could find in Chicago. It's in Andersonville on the north side. It's actually probably not a neon sign, meaning it doesn't use neon gas. You can see from the bottom here, the spectrum of colors. We have red and green, but not so much blue. So this is actually probably a neon sign in quotes, but really a mix of gas of argon and mercury to make those kind of colors. The neon colors you see at the bottom right there would be more orange. And actually in my research, we've encountered the exact same kind of emission randomly, but this is a process that's always happening. For example, when you have strong electric fields, like with my high voltage supply that I put in a vacuum chamber, some of the residual gas that was left over with my high voltage supply was actually arcing to other parts that were grounded inside the high voltage supply, and you get this beautiful picture of a corona, but not so beautiful to your detectors, right? But there's still the same phenomenon happening here to create this emission. And so I want to point out to you that with a different type of lens, you can see through opaque objects, such as the X-rays. And so this is actually the picture of the Milky Way center in X-rays that shows us that the gas there is millions of degrees hot, right? Not like the surface of the sun or other stars or your filament, which is thousands of degrees or 10,000 degrees hot. This is millions of degrees hot in the center of the galaxy, right? And you also know X-rays can see through opaque objects because of your experience with X-rays and medical imaging. So this is a photo of Röntgen's original picture of an X-ray of his wife's hand when he discovered X-rays. You can see that the X-rays pierce the opaque skin, right? But don't go through the bone, which is denser. Okay, and so you can see the structure of your bone inside, and you can even see the wife's ring there from Röntgen as well. The other thing that changing your lens can do for you is help you observe different processes and reveal hidden structure, right? And so the central region of the Milky Way and radio waves here, the central region of the Milky Way and radio waves here shows you a new kind of process that's going on. This is something called synchrotron emission, right? That's producing these radio waves and producing these large filaments that are extremely large in size. And that's something that we might come back to in a later slide lecture. Okay, so this hopefully convinces us when you change your lens with different kinds of light, you can see different things, right? And I'm going to take you to the highest energies. Let's put on the highest energy go to the highest energies we can with gamma rays. Let's put on our gamma ray lens and see what the universe looks like, see what the sky looks like in gamma rays. And so this was actually what Fermi Gamma Ray Telescope did. It measured the entire sky at the highest energies of gamma rays it possibly could. And it revealed very interesting things about the universe that we didn't yet know, right? This is the galactic plane. This is the Milky Way of the galaxy. Just like that optical image, it's glowing in high energy gamma rays. And so one thought should cross your mind, well, maybe it's just really hot gas. Maybe the X-ray gas in the center is actually extremely hot. It's much hotter than we thought, right? And it's emitting this gamma ray emission. Or maybe there's crazy fields, electric fields or magnetic fields at play that produce this gamma ray emission, like the neon spectrum. And so when you compare that to the optical emission, right, you can see that, in fact, the Milky Way as a disk is glowing in all different wavelengths. But you can learn about what's happening by going to the highest energy gamma rays, right? And so what we know now, fast forwarding to what we know now, we know that there's sources in the Milky Way that have a ridiculous amount of energy that are producing this gamma ray emission. You have things like the Crab Nebula. This is the birth of stars, right, happening in this region of space, producing this gamma ray emission. You have systems where one star is basically eating another, right? All that matter is falling into that other star, producing high-energy particles that we observe with the Fermi Gamma Ray Telescope. But then you also notice above and below the Milky Way here, there's little red dots, right? There's also gamma ray emission across the universe that's not just at the center of the Milky Way, right? And this is from other galaxies, like M31 here. And also, this is not an actual photo, this is an artist's rendition of a supermassive black hole. And so when you look at the high-energy universe, you discover new things, right? You can see things that just totally ground you in the reality that the universe is producing tremendous amounts of radiation of high-energy gamma rays. And so to really understand what's happening to produce all that emission in the Milky Way, we first have to talk about and go on a little journey about what was the state of things when the discovery of gamma rays? Was this something that we always knew? Or was this something that came out of new understanding and new detectors? And so the discovery of gamma rays actually it's one of the later kinds of radiation to be discovered. X-ray photograph that I showed you before was in 1895. The discovery of gamma rays was actually in 1900 by Paul Villard using radium salts, right? And so you can see a nice picture here of Paul telling one of his graduate students to put a hand in front of this camera to block that dangerous radiation. At the time they didn't know it was dangerous. And basically he's saying, I swear you can see the bones of your hand. And this graduate student's like, no way. So he puts his hand there. All right. But what we learned was that radiation comes in different forms. We knew that there was different amounts of penetrating material that alpha, beta, and gamma rays could go through different kinds of material, right? So this was a classification we invented to describe the different kinds of radiation that we were discovering. We know now that the alpha radiation is actually the nucleus of a helium atom. We know that the beta radiation, which goes a little further in penetrating then the alpha is electrons. And we know that gamma radiation is actually photons or light. That's what we know now. But at the time, this was just discovery. This is all something that was, what's going on here? How do we understand what's happening? And we also know now this is dangerous. We don't do this anymore. We have protection where you put material in front of most of your body when you're doing x-rays, et cetera. But at the time, from the nature of discovery, it was very important. We thank them for their service. So now you should ask the question, does this mean that all of this emission in the Milky Way is just from a bunch of radioactive radium just sitting there in the galaxy? The answer is no. I wish. That would be really easy, right? Then we wouldn't have been through all of this 100 years of discovery. So in order to understand that image and understand gamma rays, we have to go to energy. Okay? So we know that gamma radiation comes from unstable atomic nuclei, right? That's what we knew at the time. And that means that when you have a radioactive nucleus decaying, it produces this radiation. So you can take an example of cobalt-60, where you have this nucleus made up of neutrons and protons, the nucleus of an atom, decaying into a nickel-60 through one kind of radiation, right? And then that nucleus, that new nucleus that's produced from this radioactive decay, doesn't like the state it's in. It doesn't like its quantum state, so it relaxes and emits energy in the form of photons or light, gamma rays. And this is something that we'll have to use throughout the lecture series as a unit. It's called an electron volt, or mega, and specifically for these gamma rays, this is mega electron volts. Okay, that means millions of electron volts. The way you should appreciate and understand what a mega electron volt is for this gamma ray is if you take an electron and subject it to 1 volt, you would have 1 electron volt of energy, right? But here we're talking millions of volts, right? You know that your outlet is at around 100 volts. This is millions of volts for a photon, for a light ray. If you want to compare that to the X-rays that pierce your skin, that's 40,000 volts or 0.04 millielectron volts. So we're talking about the highest energies that we can talk about with gamma rays with light. But another way of thinking about gamma radiation is probably more applicable to most of us, which is wavelength. What's the size of this radiation, right? Where is it concentrated? And so from that radioactive decay of a nucleus, you have the nucleus with 28 protons and 32 neutrons here, this nickel-60, producing the gamma rays. And that entire nucleus is coherently emitted from the relaxation of the nucleus, right? You get gamma rays that have a wavelength of a picometer. Okay? That's 10 to the minus 12 meters. That's a trillionth of a meter, right? And that's a hard thing to understand. A trillionth of a meter is tiny. When you look at the radio images we talked about before, those are on the order of a quarter of a meter. So just for reference, for those of you that don't like meters, you know, a person is about 160 centimeters, 1.5 meters. Some of us are taller, some of us are shorter, you know, but either way, that's the size of radio emission, is like a human. But then the optical emission from our neon was in the nanometer range, hundreds of nanometers. And then the X-ray imaging is even smaller than that. Well, this is not supposed to happen. There we go. Sorry, so let's just review these kinds of length scales. Let's zoom in to appreciate how small the wavelength is of this light. So you probably know a credit card. I expect everyone here has a credit card, right? Or at least some of us that are irresponsible have credit cards. Basically, you take a credit card and you look at the thickness of that credit card. It's about 1 millimeter. All right? If you zoom in by a factor of 1,000, you have to magnify on just the thickness of that credit card by a factor of 1,000, you get to the width of a human hair. Okay? And you have to magnify another factor of 1,000 to get to DNA. Then you can see the actual DNA that makes up all of us. And you have to magnify by a factor of 10 to look at the size of an atom. And the atom, as we talked about, made up of the nucleus, protons and neutrons, but most of the size comes from the electrons orbiting it in this cloud, right? So the size of a nucleus is a factor of 10 smaller than that DNA. And you still have to magnify by a factor of 100,000 more on top of that to get to the size of a proton, to get to the femtometer scale. And the picometer is just above this, right? It's somewhere in between, but it's tiny, right? We're talking about the highest energy things. We're talking about gamma rays that are at the wavelength scale that are the size of a proton. So if we go back and put on our gamma ray lens, we're talking about giga electron volts, which is 1,000 times more energy than the gamma rays that were coming out of the radium salts that were discovered, right? That we already know is dangerous, right? The wavelengths of these gamma rays that we're imaging with Fermi Gamma Ray Telescope is so tiny, it's femtometer scale, right? And then you could ask the question, well, maybe they're all from protons decaying, which is something I thought was really cool. What if protons decay? And so far we have evidence that protons don't decay in the universe. There are actually searches for it, and the constraint is that protons don't decay on the order of 10 to the 34 years. So that's an even bigger number. I'm not going to try to quantify that for anyone, but that's our best guess right now. But if they were to decay, you would still get gamma rays. So that's interesting. So actually, this is where I was going to see how this works. So actually what we found out about that gamma ray emission is that a proton in the Milky Way collides with a really high energy cosmic ray proton and produces something called a pion. And that pion decays and produces gamma ray emission that we observe. Let's see how I do this. Oh, whoops. So then you should ask the question, well, what the heck's a pion? And then we're finally getting to the point of cosmic rays, right? Astroparticles, cosmic ray protons. But what the heck's a pion? All right, and so this takes me to a journey about the discovery of those cosmic ray protons. To explain our high energy gamma ray understanding of the universe, we have to talk about cosmic rays. We have to talk about cosmic radiation. And so in 1785, we're talking, almost 300 years ago now, Coulomb showed that electroscopes, these interesting objects, and one of the older ones is shown here. This is from like the mid 1800s, I think. He had these devices called electroscopes, realized that these just discharge randomly when they shouldn't, just left out. And the way an electroscope works is shown at the bottom right here. You have a charged negative object brought close to this glass vessel where you have a metal piece that extends down and holds two gold leaves. And these leaves being metals, they're sort of just hang there until you bring that charged object nearby. And all of a sudden, they electrically repel each other. They go from sitting just down vertically from gravity to just repelling, almost like magic at the time, right? But figuring out that this was electrostatics. And so what Coulomb said was, hey guys, these things are just not working. I'm putting this negative charged object nearby, I see them repel, and then randomly they just stop doing that. Something's discharging my electroscopes. And everyone said, well, that's just a faulty scope, go get another one. Right? But Faraday comes along 50 years later, half a century later, and says, no, he had a point. It's happening to me too, and you guys know I'm doing a good job, right? So he says, I bought this brand new one off of, whatever website, DigiKey or, Micro Center, and he finds out that these electroscopes actually are discharging, just randomly. And that's something at the time that was very confusing. 50 years after that, Crookes, another scientist, came along and said, well, I can make the pressure inside that scope smaller and get it to discharge faster. And that was an interesting discovery, and these scopes were used for over 100 years to understand what was happening, right, and to try to figure out this magical process, this magical phenomenon. And so then scientists became even smarter with the discovery of radiation. They said, well, can we put this gamma ray source in front of our electroscope? What happens then? And so they take our electroscope, right? They make the gold leaves repel each other, tilting away. They put the gamma ray source nearby. One of the gamma rays goes through your scope, and that ionizes the air. And that ionization is responsible for discharging your gold leaves, right? So the leaves fall back together. Okay? But the thing is, Crookes and Faraday said this happens without a source nearby. They don't have to put radium near their electroscopes. This is just happening. Is there just radium all around us? Is there radioactive material? Are we all made of radioactive material? What's going on? Where is this radiation coming from? And so for about 20 or so years, it was debated, and there were two teams. There was Team Earth, and there was Team Cosmos. And you have Team Earth here with very, very smart people like Rutherford and Theodore Wolff and A.S. Eve. And then you have Team Cosmos, which include people like Victor Hess and Robert Millikan, even, who was notably from University of Chicago here, and Domenico Pancini. And this is an actual image we have taken from the time of the kind of debate that they were having. That's a joke, don't sue me. This is Rutherford on the left saying, this must be from the Earth. We know that this radiation comes from rocks, guys. This isn't a hard problem. And these guys on the right, Victor Hess, is saying, no, it's from space, you fool, right? They're trying to figure out what's going on. And so many experiments were conducted, right? We have, is this coming from the sky or the Earth? So one of the notable ones that I learned about recently that I'd like to share with you is ASE from McGill University. So he said, I'm going to just take my electroscope all over the place with me. I'm going to take it to deep oceans, away from rocks, away from things we know produce this radiation, right? And I'm going to prove to you that it's from the rocks, right? And he even calibrated against his local measurements at McGill University. So one of the papers that he published at the time that was referenced a lot was, here says how he put his electroscope in different places, and at the campus of McGill University, charging his electroscope to 100,000 volts. And he even attributes one of the most interesting things to Professor Rutherford. This is how most of scientists should write about their mentors. He says, he was good enough to assign me to the task referring to slowly passing charcoal through a coconut to determine if that could help us figure this problem out, right? But there was still radiation. And they said, well, it must be coming from the water then, guys. There must be radiation in the water. And that actually, if you think about it enough, that actually makes sense. You're just sitting here, you say, you know what this radiation is coming from rocks. So why are we all talking about it coming from space? So Domenico Pancini says, well, actually, I have a solution for you. Take your electroscope and put it in a copper box. And that's sound advice. If you're talking about scientists, as far as it goes, if you have faulty equipment, put it in a copper box, usually problem solved, right? And that's what he did. He put his electroscope in a copper box. And he found that it was less frequent, but the scopes were still discharging. We actually still do this, by the way. I don't want you to think that that's a joke. We do put things in copper boxes. One of the instruments I just flew, a lot of the pieces were inside copper box, but for totally different reasons. And so then what Domenico decided to do was, here's a picture of him in 1908, I think. He probably was actually the first to discover cosmic rays. A lot of people think Victor Hess discovered cosmic rays, but turns out it was probably actually Domenico Pancini. So he took his electroscope in his copper box, he took it out to sea, similar rate of discharge. He also at the time, a lot of people at the time were scared about Halley's Comet. I don't know if many of you might not know this, there were two comets around the 1909, 1910. Before the passage of Halley's Comet, there was another comet, and that started to scare everyone. And so there were periods of time where everyone said, well, this radiation might be coming from the comet's there, it's going to end the world, right? And this was a huge scare at the time. So he ruled out Halley's Comet. He said, look, it's not from Halley's Comet. Halley's Comet's gone. It's still there, guys, right? But he decided to submerge it inside a lake in his copper box, and he found that it was less often. The deeper he went into the lake, less time his electroscope discharged. And so he was actually the first to discover that this is related to radiation coming from space, not from the Earth. So I'd like to thank Dr. Jan, and this is through Dr. Vinderskofer, of pointing out to me, in my abstract I referenced Victor Hess discovering cosmic rays, but actually it was probably Domenico Pancini. But Victor Hess played a huge, important role in the discovery of these cosmic rays. He ascended in a balloon multiple times in like the year 1911, 1912, and determined by going up an altitude of 3 miles that it's actually so much stronger when we go up in altitude. We can get our electroscopes to discharge even faster, okay? And he did this during a near solar eclipse because also at the time people thought, well, if it's not from the rocks, it's probably from the sun if it's actually from the sky, right? But if you go up during a solar eclipse, the sun's blocked, so it can't be that either. Very smart of him, actually. Here's a picture of a guy near his balloon trying to observe those cosmic rays that they're talking about. And this is an actual photo taken of the time from his launch. And the most decisive thing was that above 1,500 meters, above about a mile in altitude, the radiation amount was just so intense, it jumped dramatically. And this was a crazy discovery at the time, right? But it totally proved that cosmic rays, that this radiation, this mysterious radiation, is coming from above us. Okay, and he actually received the Nobel Prize in 1936. Domenico passed away in 1934, and you can't award the Nobel Prize after someone dies to them. So this is one of the controversies that I'll introduce here. Also, I'd like to point out another dangerous thing that happened at this time, so we thank them for their bravery, but this is very dangerous. They used hydrogen gas when they ascended in the balloon, and if you don't know this, hydrogen gas is very explosive. We don't do this anymore, but we still do ballooning today, and we use helium instead, and I'll come back to that later. Okay, so after it was determined that this radiation was cosmic in origin, and actually Robert Millikan coined the term cosmic rays. Once it was determined they're coming from above, cosmic rays is the new term. And Robert Millikan says, yeah, guys, you got to refer to them as cosmic rays. And in 1923, he's a Nobel Prize winner too. He measured the electron charge. He found out that what the charge is of an electron. And he was faculty here at the time too. He suspected that this cosmic radiation was gamma rays. He said this is probably a neutral particle. It's probably the kind of radiation we know about. It's probably gamma rays. And so remember, they already knew this information, that gamma rays were the most penetrating, and they had already determined that these kinds of particles were also most penetrating. So that makes perfect sense. And then along comes Compton. So I hear Compton, I hear only the smartest of audience members go to his lecture series, by the way. So Compton, who I'll mention in every single lecture, actually was also around the University of Chicago at the time, and he was awarded the Nobel Prize in 1927. And he said, these particles, this radiation is not neutral. It's not gamma rays, Millikan. It is charged particles. Sorry. And so around this time, 20 years after Victor Hess discovered that these cosmic rays, and Domenico discovered cosmic rays, they had access to new detectors. They've moved on from the electroscopes, and they've said, we now have this new device called an ionization chamber. Okay? And Compton said, well, I have a cool side project. I'm going to put ionization chambers all around the world. And this is actually a map taken of the different places and sites all around the world. You can see in New Zealand down here, there's some in Australia and India where he was giving a lecture series himself, some in the Americas and Canada. All around the world, he takes this new ionization chamber to measure this cosmic radiation. And the reason is, and this is actually just a side project, he had very extravagant hobbies. But the reason is because he was trying to determine if they're charged particles, can he figure out which direction they're coming from, east and west. From the Earth's magnetic field, if they're charged, they should be deflected. So some of the interesting notes here from his adventures on this little side project was how University of Chicago and Compton himself and even Carnegie himself funded all of this different research that was happening. And so one of the accounts from the news articles at the time was that, by the fall of 1932, the death of two physicists was not the main subject of the news coverage because Compton and his collaborators were going on such exotic journeys, right? But the most interesting thing at the time was the rising controversy between Compton and Millikan. So I thought that was interesting to point out too. And so what he was on an adventure to try to prove to Millikan and the rest of the world was that I know charged particles deflect in magnetic fields. So if you take this little picture of a magnet at the top, you have a charged electron coming through and it deflects that direction. If you have a positive particle going through from the same direction, you get the opposite deflection, right? You can separate the particles. This was known at the time with beta rays. They also knew that the Earth had a magnetic field. This is also known at the time. And so his idea was that all across the globe, he could say if the Earth's magnetic field at the equator, for example, is just pointing to the North Pole, but then as I get closer to the North Pole, I get less magnetic field along the surface. If cosmic rays are charged particles, those coming from the west towards the east will be more likely to be observed than the ones coming from the east towards the west. And this is because the ones coming from the east are deflected away if they're positively charged particles. And that's exactly what they found out. They found out that there was this east-west effect, that cosmic rays are charged particles, and in fact, they found out that they were positively charged particles, right? At the time, it wasn't known if they were neutral, negative, or positive, and now they figured this out, all thanks to his little side project. There's also this latitude effect that I can come back to, but you don't have time to talk about. It's very interesting. And so that gives us a kind of sense of the state of things in the mid-1930s, right? They knew of these kinds of radiation, right? But since it's positively charged, they're not gamma rays, Millikan, they're not beta rays, they're not negative. But they're also not alpha particles, right? They're positively charged just like alpha particles are, but alpha's not so penetrating. And so this transformation happened, though, where they, in order to learn about the cosmic radiation, they invented new kinds of detectors to try to figure out this problem, right? And so one of the other detectors that came along at the time, Wilson's cloud chamber, which you can observe here as a live view of what's happening, is basically condensed gas where just all the time, there's just particles all the time traveling through this gas, ionizing the gas, and so you see actual tracks from those particles in the cloud chamber. And so that's the kinds of tracks you're observing here. And Wilson, who invented the cloud chamber, was awarded the Nobel Prize in 1927. And Millikan, who left the University of Chicago and moved to Caltech, actually pioneered a lot of the research and foundation at Caltech after moving there. It was not previously as prestigious or even known as Caltech until he got there, actually. He worked with Carl Anderson to utilize these cloud chambers to make even more discoveries. And if you want to see a cloud chamber in person, I highly recommend the event, the Southside Science Festival. Last fall, they held in that event here at the University of Chicago, they actually had a cloud chamber so you could go and observe it. So highly recommend that event. So Carl Anderson comes along and it discovers the positron, right? Remember that magnetic field the electron deflects? Carl Anderson identifies with his cloud chambers that there's, and he's awarded the Nobel Prize for this too, that there's actually an apparently easily deflected positive-like particle. And in his famous paper, they even have a reference to the positive electron, which is the proton at the time. And they knew that the positron and the proton were different things. They knew this was a new discovery. And this is an actual photo taken from the cloud chamber of the particle bending inside of a magnetic field. That gives you a sense of what kind of discovery they were making. So Dirac at the time had proposed the existence of antiparticles of electrons, which they knew about, and so this was a complete confirmation of his theory, right? And so this is Dirac, and this is anti-Dirac, who proposed the antiparticle. I can't take credit for that joke. That was actually a joke from one of my mentors at Bowling Green State University, by the way, Dr. Salim. So anyway, this is what was observed in the cloud chamber, was that this particle that was coming in bent in the wrong direction, where an electron would have been going in the other way, right? So, but it was bending so much that they knew the mass of it as well. It was not a proton. And so could cosmic rays be these positive new charged particles, these positrons? And the answer is no, sadly. I'm leading you astray, right? But the antimatter and matter that we've discovered, we know they annihilate. We know that they give you gamma rays, actually, right? And this is something that also is a subject of research in the Milky Way. There are gamma rays that are emitted, but that's not the gamma rays we're going to talk about. And positrons, like electrons, they knew are not as penetrating as cosmic. So they knew they could rule out positrons, even though it was a fascinating discovery, right, motivated by trying to understand this cosmic radiation. And so we know now that cosmic rays are protons. Protons are the nucleus of your hydrogen atom, right? Just the nucleus. You can also call them hydrogen ions then, right? And this whole journey of new detectors leading to new discoveries to try to explain, right, what's happening with this cosmic radiation. One of the new detectors at the time was a Geiger-Müller tube in the late 1930s and early 1940s, was used a lot to understand this radiation. And this allowed and sort of revolutionized this field because it allowed you to make coincidence measurements. You could put one over here, one over there, and at the same time record the track of the particle that was passing through both of those detectors. And one of the faculty here, Marcel Schein, was a part of this effort. He put these Geiger-Müller tubes on high-altitude balloons, and he flew them to very high altitudes, actually. These were the first time they could remotely, they weren't actually on these balloons, right? So this is going up to 100,000 feet in altitude. And so this is a picture of him at dinner here in the University of Chicago, I believe, with, I don't know if anyone recognizes, that's Werner Heisenberg as well. And so there was a rapid period of now discovery enabled by these new detectors, right? You have muons, which were also discovered by Carl Anderson. He discovered muons and anti-muons, actually, at the same time the year he won the Nobel Prize for discovering the positron. So muons is something I'll talk about in the lecture next week, is a heavier but weird cousin of the electron. Also, from these kinds of ballooning adventures and trying to understand cosmic rays, we had Cecil Powell at Bristol, who flew new detectors. One of the pioneers of the field, Marietta Blow, was out of Austria, developed this new kind of photographic thing called a nuclear emulsion. And so they also put these on balloons, recorded and at high altitudes to record the tracks of these cosmic rays. So that's an example of one of them there. And so you take your gelatin, this is a kind of a gelatin that the charged cosmic ray comes through, deposits energy, and then they can develop that into a film that gives you a photograph of the actual track of the particle. And this led to the discovery of pions, and actually the direct observation of charged pions decaying. Right? So this is something that was very interesting at the time to them, and a lot of discovery from these new detectors. And so throughout all of this, from the 1900s to the 1940s and 50s, we had a much deeper understanding now of what was happening, right? From that mysterious the mysterious radiation that was discharging Coulomb's electroscopes almost 100, 200 years ago. So we now understand that cosmic ray protons come in and interact or collide with the gas in the atmosphere, for example, and produce these pions. And those pions decay and can produce muons because we directly observe them, right? And those muons can decay and produce electrons. But we also know that those pions could decay and produce gamma rays. We observe that too. And those are the kinds of gamma rays that are taken by the Fermi Gamma Ray Telescope. Those are at the high enough energies that you can see those gamma rays. But muons, when they decay, they can also produce positrons in addition to electrons, and that annihilates and produces gamma rays as well. But these are not the gamma rays at the time that we now measure with the Fermi Gamma Ray Telescope, right? But from all of this, we've obtained a much deeper understanding, right, about the high energy universe and what's happening at the microscopic scale, right? All of this happening at the very tiny scale. There was no knowledge yet of the gamma ray sky, right? This was all the kinds of stuff that was figured out at the time was mostly from detectors on the ground and at high altitudes. And so I want to come back to the signatures of these high energy interactions, as we need to start calling them. You have that proton, that lowly proton with no energy in the gas, just sitting there, and you have a really high energy cosmic ray proton coming in and interacting, producing these pions, right? And so we had this whole journey from producing this gamma ray emission in the Milky Way is happening all the time, right? It's happening everywhere in the Milky Way. And these are tiny microscopic interactions that are happening. And so we transformed in this journey from the 1890s, discovery of gamma radiation, we transformed our understanding from radioactivity, right, to interactions, to high energy particles colliding and interacting, right? And so the difference in scale here is really interesting. It's mega electron volts in energy and picometer scale, right? And now we're talking about the kinds of energies that are femtometer scale or greater than GeV, billions or 1,000 times higher. And we already knew that radioactive gamma radiation is dangerous. But this is just what's naturally produced by the universe, right? This is just always happening, right? And so those nucleons, those protons colliding with each other, are producing gamma radiation that spans the entire size of the Milky Way, which is 1,000 light years. Something that is on the scale of femtometer in size has enough energy for us later here on Earth, thousands of light years away, to observe all across the sky. It's lighting up the universe. This is the high energy interaction, the high energy universe. And this is what happens when you put on your lens, right? This is what happens when you put on the high energy lens. You can see the tiniest of interactions occurring. And so coming back to Compton's little side project, right? His map around the world, what we know now is protons are colliding in the gas of our atmosphere and producing a bunch of particles on the ground that were responsible for discharging the electroscopes, that are responsible, right, for the kinds of radiation that we were observing. And so the kinds of particles there are muons. Those are actually muons that were responsible for all of the confusion 200 years ago, right? And this actually, these muons still carry the directional information. They still are created by the deriving direction of those cosmic ray protons. They penetrate the atmosphere enough, but don't make it all the way to the surface. The muons are what's created at the surface. And so this image here is actually taken from one of our recent flights of the Helix payload. We sort of just slapped a GoPro on it and said, let's take some photos of the high altitude. So this is at like 35 kilometers in altitude. And so we have to think about the atmosphere as actually a high energy laboratory, right? We have to think about Compton, right, Coulomb and Faraday, all of these scientists trying to figure out what's going on, they actually were just living in a high-energy laboratory the entire time. These particles just exist. You have these primary cosmic ray protons coming from space that interact in the atmosphere all the time, giving rise to new particles that we studied, right, at lower energy. And as you go to the surface, you have a zoo of particles that you just live in at sea level. And this is just naturally happening, right? But in order to understand this, we had to invent a whole new field of science. We had to look at particles themselves, of particle physics, to understand it, right? And so this was actually cosmic rays, and understanding cosmic radiation motivated the birth of particle physics as a field. It was an incredible journey filled with curiosity, puzzles, and drama, with new detectors leading to new discoveries, leading to new mysteries. And we even built colliders here on Earth to try to study these high-energy particles, because it was just too confusing what was happening at high altitude. To put things in space is challenging, and I'll talk about that briefly too. One of the things we built in the 50s, after understanding that these are cosmic ray protons, was the cosmotron. This is a picture, a drawing of the cosmotron in the 50s. And so we learned how to accelerate particles to higher energies, right, here at the surface to understand what was happening. Actually, one of the interesting things about this was that it could have been named Cosmic Ray in a Can instead of the Cosmotron, which I thought was really strange because that's not a good name at all, but okay. And it was a very serious undertaking to try to name it the Cosmic Ray in a Can, although I kind of like it as well. There was also this confusing thing where at the time in the US, when all of this was being discovered, the GeV, the giga electron volts, the US would use the BeV, the billions of electron volt unit. And the reason they stopped and switched to GeV, which is now what I have to use, right? The reason they stopped was because it was too confusing. But what was too confusing about it was that the British had their own term called the billion, which actually means a million, which is a trillion, so it's not a billion, right? And so there was this weird thing with, it's too confusing to refer to them as bevatrons because that's actually trillions of electron volts to our British friends. So then later the British decided, yeah, that was very confusing. We'll also use GeV, right? So I thought that was an interesting tidbit too from history. All right, so let's come back to what really is the high energy universe. It's a place where the nuclei of atoms are just moving nearly at the speed of light. And so one of the ways you can write this is in percentage of the speed of light. And we've measured particles now coming from space that are moving at this percentage of the speed of light, right? It's just so much energy, so fast. And these are still particles. They're not gamma ray photons. These are particles moving. This is also a place, this is a universe, right, where the interactions create many unstable particles, that zoo of particles at sea level, right? And that we'll explore that a little bit more throughout the series as well. You want to think of the gamma rays here as bulldozing, right? You don't want to think of them as something you can see. They're just blowing apart nuclei on their way out. They're ionizing gas, right, and air as they travel through it. And the environments that create such particles are extreme and dangerous and baffling. They're just amazing, right? And we'll revisit that later. It's a violent and chaotic place, and it's something I love. But in order to see it, in order to understand it, we have to put on our high-energy lens. And so I want to give a little history, just briefly, on cosmic rays and ballooning, right? So we still do ballooning, just like Victor Hess did over 100 years ago. Now we're a little smarter, and we use helium gas instead of hydrogen, right? Because I said it was explosive. And so here's an example of one of the recent balloons right here out of UChicago that was built, Helix, and as well as Pueo. This is a lot of the guys from NASA filling up the helium inside of the balloon in Antarctica, where we launched Pueo just 3 months ago. And the University of Chicago has actually played a leading role in the development of this for 100 years, right? This is a picture of Dietrich Müller, Peter Mayer, and Simon Sorty, who are all faculty here and that flew many balloons in the 80s and the 90s. But in order to learn more about cosmic radiation, we had to start putting these detectors in the atmosphere. That's what motivated the continuing of the ballooning, right? And Peter actually was able to put, I think both of them together, Peter and Dietrich, actually put one of the first cosmic ray detectors in space as well. So we need to put these detectors in space to understand cosmic rays. So we put them on balloons, but we also need the experiments running controlled on the ground to understand the particle physics aspect, right? And so that's what a lot of other people do at the University of Chicago that I don't have time to continue to talk about. And so one of the challenges of ballooning, right, is effectively you're putting things at such high altitude now that you're putting your detectors in space. right? And that's a dangerous place. That's an extreme and violent, dangerous place. You have cold and violent shifts. You have things that are getting too hot when they're facing the sun and things that are getting too cold when they're not. And so your electronics, your detectors are subjected to these intense environments, right? And you have no shielding from the highest energy particles, which makes sense because you want to detect them, but at the same time, you can't just go there, right? You have to be shielded from them, right? And one of the other challenges of ballooning is the recovery of your instruments and your data once you take it, right, of detecting these particles. And this is actually much easier than before, right? Now we have people like my collaborator Dennis recovering the Helix science flight computer data here on a glacier on top of, in Canada from that flight in 2024. And then we even have just a little bit over a month ago, Pueyo's recovery near the South Pole. It was so close that they just kind of drove trucks out on the Antarctic ice to recover the instrument. All right, and that picture was just taken a month ago or so. This is also something I love, is the ballooning in the high energy universe, right? This also birthed gamma ray astronomy. And so that was also an incredible journey that was filled with puzzles, drama, a bunch of curious things. One of the most interesting things that I could find was Vela satellites that were launched, a top secret mission to try to figure out during the Cold War who was actually building and where the nuclear weapons, right? And this was what led to the discovery of gamma ray bursts in the sky. So that was the main driver for trying to for the birth of gamma ray astronomy, was that these gamma rays are coming from the sky, right? And this was also a story of new detectors, new mysteries, new discoveries, such as the Vela satellite. And so we learned that cosmic rays are not just protons along the way as well. We learned that they're also the heavier nuclei of different atoms, but they've been accelerated to such high energies across the universe that their electrons are just ripped apart. It's just the nucleus left, right? And actually, in a later lecture, we'll explore a little bit more about this composition and how we know that cosmic rays, compared to solar systems of all the different elements that we've measured so far, make a periodic table of the origin of elements in our understanding of the universe, right? And many balloon flights and space missions have contributed to this kind of understanding. So, just want to leave you off with, what will this series cover? Trying to motivate you to come back next week, right? The cosmic ray muons is something I'll talk about next week, and how they probe dense objects here on Earth. And then we'll talk about neutrinos and how they probe even denser objects than muons. Then we'll talk about cosmic ray air showers and how they may be responsible for lightning. We're going to talk about how cosmic rays impact life and maybe are related to the origin of life. Then we're going to talk about how we can use cosmic ray isotope measurements to understand our Milky Way. And then I'm going to have my collaborator Peyton Linton talk about using cosmic rays to search for water on the moon, which is a new proposed lunar orbiter. And then I'll end with the highest energy neutrinos from that Pueyo flight and how we use those to understand the most extreme environments that we know on Earth. All because we're going to put on our astroparticle lens, right, to understand them. So thank you. Whew.